Everybody, you sitting comfortably? Because we're doing circle theorems today. Again, GCSE Maths higher only, and I should say this wonderful PowerPoint was found in the Bells High School. The link is down there at the bottom, but it's very small. I'm also going to put it in the description of the video to find it and to find their website, etc. Search long and wide for a good one, and this is a good one. So circle theorems, I kind of think this is the toughest thing in the whole GCSE higher syllabus. I think each of the theorems that we'll come across are okay on their own, but the way that they're represented in questions, as you'll see later on, kind of break the brain a little bit because there's an awful lot of moving parts. So it will look similar to an awful lot of the like angles types questions where you'd solve the shape, find all the angles, and then see which one they need. It's a bit like that come the end of it, but well, you'll see as we go through. You're probably going to have an awful lot of questions, which is good because we're going to work through them when we get into class. Okay, let's make a start. First thing we're going to do, we're going to look at the parts of the circle and remember what they're called. So, that's a circle, and round the outside of the circle is called the circumference. The bit lying straight through the middle from one edge of the circle to the next is called the diameter. And half that, so from the middle to the edge, is called the radius. A line that goes from one side to the other without going through the middle is called a chord. And a chord will split a circle into segments. The bigger segment is called the major segment, and the smaller one is called the minor segment. Similarly, that's the major arc and the minor arc. Last but not least, we have a minor sector and a major sector. So if I cut a piece of pie, I'll have a smaller bit and a bigger bit, unless I cut it straight across the middle, in which they're just semicircles. But I will then have a minor sector or a smaller sector and a bigger sector. This line that touches just one part of the outside of a circle is called a tangent. There's all the terminology. We'll be using these an awful lot as we go through. Have a look through and see if you remember it. The tangent touches one part of the circle only once, doesn't pass through it, just touches the outside of the circle at one point and then goes through. Okay, let's look at some terminology with sound effects. So I've cut out a piece of pie here, okay, and we say this: the arc AB subtends angle X at the center of the circle. So it's the bit that has angle X at the center. We could also say that arc AB subtends the angle Y at the circumference. So you've got an arc, you've got the name of the angle, and you've got where it goes to. Okay. We could also say, instead of the arc AB, we could say the chord AB subtends angle X at the center, and similarly chord AB subtends the angle Y at the circumference. It might also look something like that, so not necessarily directly above it, but it could be, as long as the points are at A, B, and it goes to the circumference, it would be described the same way. So the arc AB subtends angle X, an angle Y at the circumference, angle X at the center. And you could also say the same thing about the chord. It could even look like this. So they've turned the circle around the other way. AB is still this common for both points, and we'll come to this later. There's another special rule about these points. Okay, Theorem 1. Measure the angles at the centre and circumference and make a conjecture. Now I'm going to stick this in the notes if you want to play along. You can pause it, okay, and find something out. So you get your protractor out and measure them. But what you will find is that this angle here is twice the size of this one. Okay. And I've put up all the different ways they'll use to represent that. Easiest one to see is that one. So we've got the 2 points, we'll call them A and B if you want. One goes to the centre, one goes to the outside. That angle is half the one in the middle. They might make it fatter and move it over a bit. Looks like that. Right. 2 points. Point there, point there. One goes to the centre, one goes to the circumference. that is twice that. Same thing. 2 points are common for both lines. One goes to the centre, one goes to the outside. The one that hits the circumference is twice that of the one inside. These ones below, look at it the other way. So we have in a major sector, this angle here is twice the one at the circumference. So this one in here, even though it's bigger in these cases. See where it's over 180 degrees, it's still twice the one that's there. Okay. Okay, so we say the angle subtended at the centre of the circle by an arc or chord is twice the angle subtended at the circumference by the same arc or chord. Angle at the centre. And those are all the ways that you can represent it. And this is one of the things that makes circle theorems so hard, is because it looks totally different so many ways. Watch this one for later. It marks this one, right? Where it's a semicircle, and see, we'll come to it in a second. As it's pointed out in these ones, in these cases they're all minor segments, but this one's a major segment, and angle X is subtended in a minor segment up there. So here's some questions. Find the unknown angles giving reasons for your answers. Pause the video, and you'll find that the answers are this. So if that angle is 84, and both points share the same root of AB, then this angle is going to be half what's in the centre, so it's going to be 42 because of the angle at the centre. This one's the same thing. Here's points going to the centre, points going to the circumference. The angle at the circumference is half that of the centre, so angle Y is going to be 70, and hopefully you got those answers. Here's another couple. Find the unknown angles given reasons for your answers. So X and Y. Okay. Little bit harder, because they don't give you X or Y in this case. They give you this to start off with, and what can you tell me about that shape there? Well, it's an isosceles. So if that's 42, that's 42. If I add those two together, I will get 84. And then I take 84 away from the 180, and that will give me X, which is 96. And if I know that's 96, I know the one at the circumference is half that, so it's going to be 48. Similarly, in this case they give you the angle at the circumference, so it's going to be half that of the middle, so P is going to be 124. And then we know that this bit in here is a isosceles triangle, so Q and this angle here are going to be the same. So we do 180, take away the 124, gives us 56. And then we'll divide that by 2 to find the size of each angle out. And that would give me 28. Lovely. Let's go to Theorem 2. The angle in a semicircle is a right angle. So this is the special case we're looking for. So we don't have a major or minor sector here. It's just split straight in the middle. What size is that angle? Well, it's 180 degrees. So any of these lines that go sharing the same point, call them MB, and touch the circumference, touch the circumference, touch the circumference, are going to be half that there. So they're all going to be 90. Like that, and like that. So like I say, can represent it each way, but remember it's sharing the same common point on the chord, and then touch the circumference. And those are going to be half of the 180, which is 90. This is just a special case of Theorem 1, and is referred to as a theorem out of convenience. So we call it Theorem 2, even though it just is Theorem 1 in practice. But it's another quick and easy way to look at it. Okay. So find the unknown angles below. State any reason. We're going to start with angle A. Where's angle A? It's up here. We have a semicircle. Angle, their lines touch the circumference. A is just going to be 90 degrees. Angle is a semicircle. Angle B. Similarly, we've got a diameter. Splits the circle. We've got a lines touching the circumference, so it's also going to be 90. C is going to be 20. Well, why? Well, we have a triangle here, and angles in a triangle add up to 180, so we have 90 plus 70 is 160. Add the 20 is 180. Angle D. What are you going to tell me? You're correct. It's 90, because we again have our diameter here. We've got lines going to circumference, so it's going to be 90. And last but not least, angle E. This is a triangle with a 30, with a 90, that's 120. That's going to leave me 60 left over for the angles that sum up in a triangle. Theorem 3. Angles subtended by an arc or chord in the same segment are equal. So, if I have lines going from a chord down here, excuse me, take a drink. That's what you get for eating Subway just before you go to record. It was really nice, I must say. Italian BMT, very very nice. So we would have the same points. Both these angles that are subtended here originate on the same chord or the same arc or whichever way you want to look at it. And if they go to different parts of the circumference, those angles are equal. You can even go down there. So all those three angles are the same size. Now they may not look at you looking now, but if you got them out and measure them, or you try this experiment, draw yourself a circle and do this experiment, you will find that they are all the same. So it works for an arc or chord, whether it looks like that or that, turn it the side, both those angles are the same. Now they look totally different, and the look of this diagram looks completely different to those, but what you're looking to see is, does Theorem 3 fit? There's your arc chord. Similarly, because we have a chord or an arc here, these two angles will be the same. They'll be equal to each other, and we'll call them y in this case. Okay. Find the unknown angles in each case. So it's giving you actually the complete the same layout as before. So we know if this is 38, then these other angles must be equal to 38 because they all originate on the same chord or arc. Similarly, this one over here, x is going to equal 30 because those 2 points are those two angles subtend from the same arc or chord, and that's going to be 40 for the same reason. These y is subtended by the same arc or chord as the angle 40, so then y equals 40. Theorem 4. The angle between a tangent and a radius is 90 degrees, called tan rad for tangent radius. So if we draw in a tangent there, remember that's the line that only touches the outside of a circle at one point, and we draw a line from that point to the center, that's going to be the radius, the angle in there is 90 degrees. So let's see how this works. Could draw it like that, could draw a tangent that side. If it looked like that, that would be 90 degrees. Let's test it out. If OT is a radius and AB is a tangent, find the unknown angles given reasons for your answer. Okay, we're going to start with angle X. Well, the first thing we can say is that this angle OTB is going to be a right angle. And if we know that's a right angle, then we can add 90 and 36 together to give 126. And then we can take that away from 180 because that is a triangle in there. So 180 minus the 90 minus the 36, and that will give me 54. Great, easy peasy, no worries. Angle Y is next. Well, what can you tell me about this shape here? You can see that that has a diameter there. So the angle that's subtended in a semicircle is going to be 90 degrees. Angle in a semicircle, like from before. And if I know that's 90 and I know that's 30, then to find Z, I do 180 minus 90 minus 30, which will give me 60. Number 5, the alternate segment theorem. One of the things the hardest spot. So the angle between a tangent and a chord through the point of contact is equal to the angle subtended by that chord in the alternate segment. So what does this look like? We have an angle that goes between a chord and a tangent. Okay, if I do another angle subtended to the circumference from that same arc or chord, then this angle equals to this one. Similarly, this angle, the lines that are going to, or the angle subtended is actually this one here, and the one at the top there is also going to be equal to y. And that can be the hardest spot. I think of all the theorems, this is the hardest spot, because look at all the examples we've done so far. There's been a bit of circles with major and minor sectors. There have been angles equal as long as they share the same arc chord. They have been triangles involved, so your knowledge of triangles comes in the shape play. And we're going to add a few more on off this, but by the time you look at this kind of shape, you're going, well, I see a triangle, it's got to be something to do with the triangle. No, there's a tangent here, well, I'm going to use my 90 degrees. I don't. Here it is. So, find the missing angles below, given reasons in each case. So we'll start with x. Well, we have a chord here, and we have an angle between the chord and the tangent of 45 degrees. If I use that chord and find the angle subtended by that at the circumference, it's x. So x is equal to 45. Similarly, we know this is 60 up here. That is the angle subtended by that chord or arc. So that's equal to the angle between the chord and the tangent. So y is equal to 60. And we have a straight line here with 60 and a 45, which is 105. We take that away from the 180 because it's a straight line and make it 75 degrees. Are you crying yet? Remember, we're going to practice all these, and I'm going to give you some tips for working through that. Actually, have a one sheet that contains all the theorems within inside, but you need to understand what the theorem is, because as you can see, the description of it in words is nonsense until you can actually visualize it or see it. Let's go for Theorem 6. It's a cyclic quadrilateral theorem. Quadrilateral, you say? What are you talking about? Well, it's a cyclic quadrilateral. So the opposite angles of a cyclic quadrilateral are supplementary, as in they add up to 180. So a cyclic quadrilateral is any four-sided shape that you can make by 4 points within a circle. So as long as the 4 points touch the outside of the circle, that's known as a cyclic quadrilateral. And what we find out is that opposite corners equal 180. So w and x, if I add those together, will give me 180. Similarly, y and x, because they're opposite each other, will also give me 180. There's another example. P and Q would be 180, and R and S would be 180 because they're opposite. Let's see if we can use these as examples. So the first one, we have to find out x. Well, we know this is a cyclic quadrilateral because we've got 4 points on the outside, and we know that these opposite angles are equal. So we know that x and 85 add together to give me 180, and if I work that out, that will give me 95. Similarly, we know that y and 110 give me 180, so y will equal 70. In this case here, we have a four-sided quadrilateral. We've got to work out p first. Well, we know we can work out p because we've got a straight line here. 135 plus p is going to give me 180. So if I work that out, I will get that p is 45. And then I can use my opposite angle theory from a cyclic quadrilateral. So q's next. So if 70 and q add up to 180, so 70 away from 180 is 110. And similarly, we know this is 45. We know r and p have to add up to 180, so that's 180 minus 45, which is 135. We are nearly there. The two tangent theorem. So if we have two tangents and we put a point anywhere outside the circle, the only two tangents that can be drawn are going to be equal in length. So if I have a circle with point P and I draw a tangent to the circle here and here, these two lengths QP and PQ are going to be equal. And the reason that this is helpful is because this makes an isosceles triangle. If I join Q and T together, we get an isosceles triangle here, and it helps us work some things out. Similarly, here's another example with P up there out of the way. The two tangents, PQ and PT, are going to be equal. Let's look at an example, and you're starting to see the complexity of what these bloody things go by. We have got angles subtended all over the place. We've got tangents. We've got points outside the circle. It says that PQ and PT are tangents to a circle with center 0, or O. Find the unknown angles given reasons. So W, start here first. We have a tangent and a radius. This angle must be 90. Using the tangent and radius rule, or theorem should I say. X. Well, it's the same thing. We've got a radius, we've got a tangent, so x also must be equal to 90 using the tangent radius rule. then we have y. We have qt, we have an arc, and we have an angle subtended to the centre of 98 and an angle subtended to the circumference of y. Y is going to be half of 98, which is 49. One last thing to do. We've got a cyclic quadrilateral here. Now, this may look a bit odd. It's not really a cyclic quadrilateral. It's just an ordinary quadrilateral. But we know that this is a four-sided shape, and that the four-sided shapes all add up to 360. So our opposite angles don't have to be equal, but in this case they are. So we know that x and y are both 90, which is great. We know that that is 98. So we take those 3 away from 360 and we get 82. Okay, so it's not a cyclic quadrilateral because the p doesn't lie inside the circle, but it is a quadrilateral, and all quadrilaterals have 360 degrees anyway. Nearly messed that one up myself. From any point outside the circle, only two tangents can be drawn. They're equal in length, so we can use it to solve this. So we're going to start with w. It's 90 degrees again because of the tangent radius rule. We've x. Well, we have a triangle here. That's 90, that's 50. X is going to be 40 because that's what's left over. With angle y, we have a tangent. Oh, that's not actually right. That's not how we're going to solve that. I thought we were going to use the theorem rule with the angle between the chord and the thing, but we're not going to do that because that would give me that one. What we're going to use is the fact that we have an isosceles triangle here. So we've got a tangent. We know that PQ and PT are going to be equal, so this is an isosceles triangle. If this is 80 degrees, then y and this angle here must be exactly the same. So we're going to split the 100 degrees left over from a triangle in two ways, and we're going to get that y equals 50. Again, nearly made a hurlers of it. And then z. How are we going to work out z? It's your alternate segment theory. So we have a chord here of, for an angle here between the chord and the tangent of 50, right here, and that chord has an angle subtended to the circumference. So it's going to be, these two angles are going to be the same, and voila, 50 degrees. Tough. I have to say, even I find this tough because visually there's an awful lot in that. There's an awful lot of moving parts, and there's an awful lot of things that you think you see as you're going through it. Now, the trick is this. Start with Theorem 1, go to Theorem 2, 3, 4, 5, 6, 7. Know your 7 theorems. If you can put a number to them or put an order to remember them, all well and good, until you can get comfortable enough to think what they are. Work your way down and see if anything fits. Does that apply? Does Theorem 1 apply? No, it doesn't work on the Theorem 2. And see if you can work your way around the shape to the point where you can see what helps you really, more than anything else. So yeah, nearly there. Theorem 8 is a chord bisector theorem. I think this one's a little more straightforward. It says that a line drawn perpendicular to a chord and passing through the centre of a circle bisects the chord. So if we have a chord like that, and we draw a line from the radius at 90 degrees, this line splits equally in two. So if I have to find the length OS, well, I know that that line there cuts this line 2, it's 4. And we can use that length 3, that length 4, we can use Pythagoras theorem. It's a 3, 4, 5 triangle. OS is 5. It's Pythag triple 3, 4, 5. So go to 3 squared plus 4 squared equals this squared. It's 9 plus 16. Square root of 25 gives me 5. A line drawn perpendicular to a chord and passing through the centre of a circle bisects the chord. In this example, find the angle x. Well, we know that it bisects the line there, but it also gives me the same angle here and here. Now, if that's 22, then that's going to be 22. We know that that angle is 90, but 90 plus 22 is 112. That whole triangle is going to add up to 180. Therefore, we know that 180 take away 112 is going to give me 68. Here's some mixed questions. Throwing them all together again. I think my head's going to explode. If you want, I'll work. Well, I'm going to work through this at the start of class next week. PTR is a tangent line to the circle of T. Find the angles SUT, SOT, OTS, and OST. Whoa. Right. Start with the SUT. We have an angle between a chord and a tangent here of 65. That's the only thing we've been given. So it's fair to assume that this is going to be our starting point for working something else out. So there's only one of the rules where this helps us, and it's the one that says the angle between the chord and the tangent is equal to the angle subtended to the circumference from that same chord. So there's the chord, the ST, that the 65 angle comes from. The angle subtended is up there, which is SUT. So SUT is equal to 65, and that's our starting point. That's our alternate segment rule. The next one is SOT. Okay, SOT and SUT have something in common. They have the same arc or chord, and the angles, if one gets subtended to the center and one gets subtended to the circumference, the one at the center is twice the size of the one at the circumference. So SOT is equal to 2 times 65, which is 130. OTS. We know that the lines between, that's a radius and a tangent, we know that they cut at 90 degrees. So if that's 90 degrees in there, then the angle OTS is going to be 90 take away 65, which is 25 degrees. That's their tangent radius rule. And last but not least, OST. We can just use the triangle rule. We know that SOT is 130. We know this is 25. 130 plus 25 is 155. So that's going to leave that to be 25. We also could have said that this is an isosceles triangle because they're both radius, and those two angles are going to be the same. Either way, we would get 100 or 25 degrees for that angle. One more. PR and PQ are tangents to the circle. Find the missing angles giving reasons. Angle W. Whoa, whoa, whoa. This is crazy. Angle W. Okay, let's start off. It's going to be 22. Why? We have a cyclic quadrilateral in here. Okay, so we know that the 110 and this in here add up to 180. So we know that this whole bit in here is a 70. So 48 plus what gives me 70? 48 plus 22 gives me 70. What about in here? Isn't this great fun? It's going to be 68, right? Because of the tangent and the radius. We have got a radius and a tangent here. That's 90 degrees. If we know this is 22, then 22 plus what gives me 90 is 68. Sure enough. We're going good so far. Maybe, maybe not. Okay. Angle Y. Well, what do we know about angle Y? Well, angle Y is part of an isosceles triangle. And the isosceles triangle goes like this. So UP and PR are exactly the same length. Okay, and we know that X is 68, so the angle PUR must be 68 as well. So 68 and 68 are 136, and I would take that away from 180, and I'd be left with 44. And last but not least, we've got angle Z. I actually think angle Z is okay, because this is going to be 68 because of your alternate angle. We've got a chord, we've got a tangent. This angle here is 68 between the chord and the tangent. The chord subtends an angle at the circumference, which is Z. These two are equal. And that's it. And you can see how with so many moving parts, I actually think that question is a little unfair because the tangent should really continue on further on that way. And that's the end of circle theorems. We're going to practice them. We are going to get very confused. We are going to fight. We are going to trip up. We're going to do all those things. And we're going to try our best to solve these things. Some of them are going to be easier than other ones. Some are going to be harder. Remember that the hard questions come in the last couple of sections of the paper. And it's about scoring points at that stage. Okay, I'll see you in class on Tuesday. Take care. Speak to them. Bye.